And maybe you want to turn to the first slide and start to, go into full screen. And then I'm going to introduce you to the audience. Okay, and good morning, good evening, and also good night to our online audience. And thank you for being with us in the very last week of this year. And thank you so much for sticking to it. And it's my great pleasure to have Peng from Northeastern University, who is now a postdoc researcher in the Department of Electrical and Computer Engineering. So Peng's research focuses on security, privacy, and trustworthiness in distributed intelligence, with applications to mixed reality attacks, multi-agent and robotic collaboration, and privacy-preserving machine learning. And interestingly, beyond academia, Peng also co-founded a startup, a AI-driven platform that optimizes and automates online advertising for agencies and e-commerce business, serving as its chief scientist. So I hope we can learn something both for our research and for managing a startup, from Peng's talk. Yeah. So now, Peng, please take it over.
Okay. Thank you, Tao, for this kind introduction. So today I'm going to talk about two important pillars in the trustworthy AI. One is the postdoc, my postdoc work, mixed reality assurance, and also another work is in my PhD. My advisor Paul Closses, I think, is also here. So it's talking about the federated learning. Okay. So this is agenda today. I'm going to talk about the mixed reality and later the federated learning. So why we talk about the trustworthy AI right now? So we use the AI every day, and it's very important. Like we know that how to build the AI that is reliable, that is security, that is trustworthy for the human beings, right? So it usually so we can categorize the trustworthy AI in 6 pillars. But there are different categories. Generally, it can categorize into like the AI must be fair, robust, and then also need to consider about privacy, secure, responsible, and also the transparent. So for this talk, we just focusing on the 3 part of them, like safety, robustness, privacy. But all these 6 pillars are interconnected. For example, that if without we can withstanding the adversary attack with robustness, the system can be secure. Also, the privacy the same, that if violate the user's privacy, this is not a trustworthy system. So let's talk about our first pillars, mixed reality assurance. So how this can be contributed to the trustworthy AI. We have witnessed a significant trend that recently that the virtual reality is evolving into the mixed reality. For the people who not familiar with virtual reality, this is kind of like the people like wear the set that they only can see the virtual environment. But the mixed reality right now is kind of like the mixed with the virtual and the reality. Like this figure showing that we can see the real environment. Also, there is some like display that virtual sense can guide you to do something like more information can help you. This is very critical in the high stack environment. For example, in the defense, it's evolving from the we are only doing the training rehearsal to the MR heads up overlay that they can do this. This can help the searchers to do the faster decisions. And in the healthcare that we are training to the MR surgery guidance directly. And also, I'm not sure you guys have heard the news. The metaverse that is really big sense. But recently, Meta just announced that they will cut a lot of budget on the virtual reality, because it's hard and it's not like a user friendly sometimes. And but they invest a lot of money into the mixed reality, like the Meta Glass. If you heard about it, it's pretty cool. And so this is the significant trend that from the recently from the VR to the MR. And we did it in my postdoc work. We did some work about the mixed reality, about the security. So so moving from the VR to the MR also bring the a new threat in this challenges. There are three threats that we most care about. One is adversary manipulations. That is intentionally that hijacked maybe by some hackers. They can manipulate our system parameters, like the change the brightness of the VR set, MR set, or like inject some like fake thing, fake object that can disturb people's another threat is called the system limitation. That is naturally it's by itself. Like during the tracking, it has a tracking drift and the position calibration errors and the rendering instabilities. Also some like a sensor a noise, something like that. Another threat is called the environment same factors. It's it's embedded itself because that if you use the virtual realities, it's it's like if there are so many of the complexity of this scene that you may feel uncomfortable, and also it's low the frame of or contrast of the scene environment. So this threat can have a cognitive impact on the human because human wear this MR set. I think most importantly, the cybersickness. If you have used that, cybersickness is the most critical one, and it also can reduce the engagement and impair the decision making. So let's talk about cybersickness in the MR and so I use the VR set before when I play games. It sometimes if I play some like a fast motion games, it can cause me nausea, disorientations. This is I play games, but in some mission, like that's very important. And like if you feel dizzy or feel nausea, that's a we should avoid that because if especially for DoD, you are in a mission. So how we do to do that? Traditional approach is that they just I think it's just waiting the symptoms to appear, then they are tuned to try to stop. But in our recent work, we are beyond of this simple predictions, like symptom moving beyond the symptom prediction to formal probabilistic guarantee of this type of sickness. What we want to do is that before people really feel sick, and we can alert, we can show the evidence that okay, this is you are going to go through the high subsequence with the probability with a high probability. So that's then we can mitigate this mitigate this threat to reduce this subtext for the users. So it's like this probabilities are giving this fast motion sickness. That is a metrics that measure the subsickness of the users in this immersive environment and giving the evidence. So the evidence can be also the hard and the soft. The hard, I will going to talk about what is the hard soft evidence means that sometimes that luminance can be so it says that luminance must be bigger than the level 3, and the soft evidence something like they have some it's a noise, for example noise, and it has a distribution of it. It's not it's not a determinist. So and if it's violated this violated it's a threshold, it will track the mitigation. And for example, we can reduce the luminance, simplify the sense, and then we can alert the users. We in our ISMA paper, we published in ISMA, and we build a Bayesian network, and with this probabilistic verifications to do this safety check for the mixed reality. So this is a overview of the probabilistic verifications, and we model a hierarchical relationship between this threat. We have a 3 threat: adversary magnification, system limitation, and environment. And then this threat has impact on the system parameters such as luminance, contrast, something like that. And these system parameters will also impact the human response, like the human there is one measurement called the GSR. That's measure the skin moisture. It will reflect the reflect the human motion changes. And finally, they will give a faster motion sickness by the users, like if you're sick or not. And then we can enable these formal properties verifications to do this safety constraint check. Like, let's go more details. So why we using Bayesian network in here, and that's because it's kind of because Bayesian network is handle the uncertainty explicities. It can model the complexity, hierarchical relationship between the systems, the human factors, and the cybersickness. So most important, and we can also provide some interpreted causal structure explain, and we can enable the formal probabilistic verifications. It means that we can reason about what if scenarios. For example, like if the system parameter changes, what is the probability of the server cybersickness? Let's take a look at what kind of Bayesian network that we have learned and we try to build for this framework. So that is a Bayesian network we build based on our data, and we can see this hierarchical structure right now. The yellow node is a parent node, is the system parameters. It can be manipulated by this thread. So and it has an impact on the human parameters like the eye openness and the skin moisture and something like that. And finally, it will have a child node, the faster motion sickness. And so by building this Bayesian network, we can to do the inference and we can to do the verifications. So how are we going to do that? So the inference part is that we compute the cybersickness view the chain rule over the Bayesian network. Like this is a simple Bayesian rule, and the cybersickness given the observation, what is the probability of the cybersickness? It's equal to the joint probability of the cybersickness and with the observation divided by this probability of the observation. This joint distributions is factorized by the network structure. So if you are familiar with the Bayesian network, this is kind of the key equations that how this Bayesian network build. And so with inference, we can do the verification queries. So we can query is a system safety. That means that we want to query the probability of the cybersickness equal to high, and giving this observation under this current state, satisfy some safety threshold. This safety threshold can be like a 0.1. So if we say that given this luminance and the cybersickness is high, the safety threshold is 1%, 10%, something like that. We will talk more about that. And we also mentioned about the hard and the soft conditioning in this evidence. So what it means, so here is the example. Hard conditioning means that the luminance is equal to 5 or luminance is bigger than the 3. It's deterministic. So, and vice versa, the soft conditioning, that means this has some distribution. It's like a sensor noise. We don't know. So it's kind of giving the distribution of it is constrained. So then after that, we can calculate the probability of the cybersickness under conditions with this joint distribution over this observation probabilities. And in the real practice, we combine this hard condition and a soft condition together as this omega evidence constraint. So this lead to us complete pipeline. That the complete pipeline is that we giving this thread that we monitor the factors, and we update the neural network Bayesian, not neural network, it's Bayesian network based on the data. And after this Bayesian network trained, and we will run their verification query based on this hard or soft evidence. And then the verification, we will see that if it satisfies some safety conditions or it's not, then if not, we will issue an alert to the users. So this is a adaptive mitigation strategies. from how it works. So it's like firstly we monitor that we do the inference, like we keep monitoring the subsequent probabilities, and then we see that if this probability FMS bigger than the probability of the 80%, then we see that we need to mitigate these high issues, because we can automatically adjust the system parameters if here is example, like given the observations. Observation is that has a high luminance, or the scene is so complex. So we will adjust the system parameters, or reduce the luminance, simplify scenes, something like that, and then we finally we will have a guarantee. Say this now it's safety insurance. So this kind of turn into the reactive. Waiting the symptom appear to the proactive. Before the symptom appear, we will give the probability set is safe or not. It's not safe. This is very important in the critical domain, if especially like a defense, something like that. Let's see some result of the how way to do this verification. What is the result? Some questions we care most. Something like first one is that which system parameters matters most. So we system parameters we care about the four system parameters as previously Bayesian network structure shown. We have four: Hawk features, luminance, spectral entropy, temporal smoothness. It's those four parameters is measure the same complexity from different perspective. So more details we can maybe later we can check our paper. So these figures shown that from the when we increase the system parameters, how this probability of the high cybersickness changes. So we can see the Hawk features change the most, has the most changes from it's I think it's the change is not much, but compared to the other parameters, it has a high impact for this probability subsickness. That means when we see that Hawk values is changing from 1 to 4, it has a high impact on this cybersickness. Maybe hypersickness with high, the probability will increase. The second verification question is that what the physiological signal matter most. We have this couple of the factors like GSR and the openness, something like that. And we can see from these figures, we see that the GSR has most, these figures is GSR, this scale moisture has most impact for this high cybersickness. That means it actually increased a lot, increased from the 0.45 to the 0.8. So it means the GSR is the most critical physiological indicator that for the safety monitoring. Means when we monitor the GSR that has a high values, that means it's most of times the user's cybersickness may be high. So we need to mitigate it right now. The second verification question is that what happens under the adversary scenario. Means that if we have the system parameters is manipulated by some hacker, so they increase the luminance to high level and Hawk value and GSR value. So what is the high FMS value looks like? So FMS value in this work, we have 7 levels, and we define that if bigger than the 4 is a high cybersickness. So this light blue we show here, like is the baseline of the FMS. And when we manipulated the system parameters and make it bigger, right, the high levels, the FMS under attack, they shifted to the high level of the cybersickness. So it means when under attack that users under this evidence, so users get it very easy to have a high cybersickness. So we needed to do some mitigation strategies like the luminance control and the scene, and we need to simplify the scene, also give the user alert, something like that. The third questions that we want to ask is that what is the safety operation range? Like we see that our safety constraint is that giving so this is low cybersickness. We want to the threshold is bigger than the 90% is 5. So we and in this experiment, we only focus on GSR since then in the previous experiment, we see GSR is the strongest indicator that of the cybersickness. So when we see that this light blue is a GSR baseline, when we inject this safety constraint that we see, we must satisfy this safety constraint. Then the GSR is shifted to the low level, means that to ensure its safety, we must say that the GSR should be below some level. So it's like below from the 1 to 3, it's like a safety range for the GSR value. So this is the first section I'm going to talk about this. The key takeaway is that we bridging the verification methodologies to the mixed reality. Details is that moving from the reactive symptom measurement to proactive, like it can mitigate the threat before people feel cybersickness. And also it's bridging the gap, pioneer the link between the noise physiological data and the formal safety constraint in mixed reality. It's also a foundation for the future. This is a baseline framework can certify safety in different applications, different AI systems, like it paves the way to the real-time like assurance. Future directions we were talking is kind of like we can do the adaptive verifications. Now it's kind of not adaptive, but the future we can do the adaptive verifications. Also, we can have some mitigation learning to do reinforced learning and the human in the loop. Also, we can beyond the cybersickness, we have a lot of others human cognitive impact like engagement, confidence, fatigue, cognitive node, and also we have some different attack. We want to say how it impact like a latency attack, like a jitter attack, something. Also, the privacy is also very important, which I'm going to talk about in the next sections. So that different users have a different MR set, how they don't share the data set but learn together. And also the different applications can be the military trainings, AR surgeries. This is a significant and like a evolving trend in this area. Before I'm going to the next sections, if anybody has questions, feel free to ask.
Yes, I have a very quick question, Peng. So when you talk about the Bayesian networks and also the inference associated with that networks, are you talking about the discrete case, meaning that everything, the entire problem setup is about discrete?
Yes.
Okay.
Yes. Yeah. Yes.
But I wonder, for example, when we talk about this mixed reality and also parameters associated with this device, those parameters can be continuous, right? Or
Yeah.
you just by default you discretize it and then everything goes into discretized domain.
Yeah, that's a very good question. Yes, exactly. There's values that are a lot of values that are the continuous, but there's this for the Bayesian network, this graded is can have a lot of beneficials like and it's easy and also kind of like simplify their computation cost. If there are so many, we have so many of the parameters, and if we to do all the continuous, that kind of training is needed a lot of time. So we disgrade it. Also the disgraded it also can help us to do this formal guarantee easily. As you see in these figures, we categorize into the disgraded levels. So that's easy to measure it to give this verification certificate. But sure, yeah, this continuous. It's also maybe it's more accurate. I think that's also a good suggestion that for the future work.
I see. Thank you. Thank you.
Mm. Okay, I'm going to the next session, further learnings. So we talk about before we talk about the human cognitive say security. So now we talk about this privacy with this data self. So why data needed the privacy is that so the data can be sensitive, right? If, for example, in these figures that in the different facilities, they have hold their own data set, the locations, such as some data locations, or the memberships, or something critical information they cannot shareable. So, but there is some common information that we want to exchange. So how we to do that? It's so that's the federal learnings that they proposed in couple of years ago. They will leave the data in local, but they will upload their model informations, such as gradients update. They will to the server they will exchange, they will aggregate information, then send it back to this local to have a better ability of their local model. So this is the conceptual of this federal learning mean. They will train locally on the client and they will share update. Then no raw data we're sharing. Server will aggregate aggregate to local model to become a global model, and global model will pass to the local again. Basically, the objective is to minimize the loss function of this combined local loss. So there are three key challenges in the federal learning. So one of the challenges is the heterogeneity, means that different client may have a different data distribution, right? So it's very hard, if the data distribution is different, it's very hard to learn a common models. Sometimes it's very hard. And another challenge is the communication. Like it's if the model is very big, recently the transformer models, the large language model is very big. So if we transmit it through it can be a bottleneck. Also, the safety and the security problems that even we don't share the data, it still has some leakage, gradient leakage problem. And also the data poisoning, some local client is a poisoning client. They can poison some data. Some also now recently the membership influence, something like that. These are all safety issues. But in this section, I'm going to only focus on the heterogeneity issues. So there are many of the articles talking about how we address this non-ID issues. So one of the approach is called the personalized federal learnings. It's before we talk about the federal learnings, learn only one global models to aggregate the local informations into one global models. But we move beyond this, and we want to that each client should has its own personalized informations. And these personalized models also can have some information from the other models. There are a couple of the approaches to do that. So they can fine tuning their local models with other informations, or they can do some meta learnings. They do some proxy terms. Also, they can do model mixing, like a model where aggregate information into this one model. But we have the high impact of the, we will emphasize the local information more than others, something like that. Another approach called the cluster federal learning. It's a middleware, like between the one global model to the personalized model. So it's for example, like if a several client has shown the similar distributions, it makes sense that they should cluster into one cluster. So this will make sure that the data is making most use of it informations. So like this figure shows that with local training and we get the models, and in the server we will aggregate it together if they are similar if they are similar. And we in our recently accepted work in the PAMI, and we proposed a cluster federal learning in under the Bayesian view. So basically that we like these figures, we have a couple of the client, and we will associate this client to the clusters. We have a key cluster in the server, and we can associate the client to any of the clusters. So there are many associations. So under this one associations, we say that client 1 or 2 associated to these clusters, and the client 3 and G will associate with cluster I. And the key clusters, there are key clusters totally. So how we going to derive this from the Bayesian perspective? So the goal, like we have this key cluster, the goal is that learn the key cluster parameters posterior. So this omega is a cluster parameters, the key cluster parameters. So it's giving the data. So we're deriving to like a basic Bayesian likelihood prior, and we will equal to this. We will formulate it as it's a mixture of the association hypothesis. So this theta belong to this capital theta. So this is all the associations, and they will the joint distribution of all the associations probabilities. And this can further derive into like this association with this weight over this p theta omega. So this p theta omegas is under this one associations of posteriors. It can further derive into this. They have a key cluster, right? Key cluster probabilities. Then the key cluster, each cluster has a couple of their client. It's like a J is a number of the is the index of the client. So this conceptual framework we factorize it from the Bayesian view from the ultimate goal to this local client update. So this conceptual framework is kind of optimal. We have adapted several simplified algorithm from this class federal learnings. So it turns out some existing federal learning algorithms, cluster federal learning, can also derive from this our framework. And more details, I think we can check our paper later. But after this, I'm going to talk about more about this, how we're going to apply this federal learning in different applications. So one of the applications we do is indoor positionings. Positioning is a privacy information that we don't want to show our location to other people's. So it's naturally that the federal learning is a good fit. We have several contributions. We proposed Bayesian federal learnings into these applications, and we using Bayesian rule to handle the long ID data. And another work we're using the uncertainty awareness in the weight update, and we gain the better performance than this just a global learning. And another applications we did is GNS JAMA and detection. So JAMA is something like when we have a satellite, right? We want to use signals to do the localizations. But if we have jamming signals, jamming signal is a very high signals. It will override this jeopardize this GNS signals. So it's important the way we need to classify it, we detect it, and then we mitigate it. So this work is just like how we're going to classify this jamming detections. It's we turn the signal into the spectrogram that they have a 6 kind of the jamming signal type. So then we will using. Well, it also has some privacy issues because different cities or different companies, they have their own. They don't want to share data. So how we contribute that how we to learn a global model or some personalized model can exchange the information without showing the raw data. So we did the global model. We also did the personalized model to contribute to classify these jamming signals. And this turns out the 3 papers we have published. Last application I want to emphasize is federal learning in the reinforced learning. what work we did is this environment. We simplify the environment. That under this environment, it's amazing maze problems that several agents explore this environment. And this yellow block means that it's an uncertainty about the environment. It's a wall or it's an empty place. We don't know. So we let the agent explore this area to see. Then each agent will have its own belief this environment. So how we're going to aggregate this belief to update the global belief. Then we use this federal aggregated approach. Also, it's using this approach has a beneficial that we don't share the locations with each other. So we just show the belief of this environment. So this is the pictures of how we're going to show it. Like this agent has its own belief that of this environment looks like, and also they will aggregate in the server. But here it also has a double counting problems because it's it uses private information each of the agent many times. So we need to remove these double counting problems. This is also important in this work. Actually, this work derived from our previous paper, Bayesian data fusion with shared prior. That's talking more detail about this double counting problems if we overuse this private informations. And the result we show that our master has a compare result compared to the others, and this is the accumulated awards with reinforcement learnings, and also the right figures show that our master can quickly to have a knowledge of this has a very good knowledge of this environment, while other master their belief of this environment is keeping low. So that means they may need more times to evolve to know the certainty of this environment. Future work we are going to talk about some we talk about the classified learning, but the previous work is all like the number of the cluster is fixed. So we want to investigate if it's an unknown number of the cluster. That's a actually, we recently published a paper about how we're using the long parametric discovery of these client clusters. And also some future works about the topology federal learnings that if we have seen that we can associate the client to the clusters randomly or some in different structure. So it's naturally how we're going to discover this structure is also important. Some application future work, we can do the policy sharing and human reported interactions with and also we talk about earlier that we can integrate with MR scenarios. So safety, privacy, important robust aggregations, leakage detections, and auditing some future works. Okay, so I'm going to finish this talk by a conclusion. So it's kind of like in the first section, we talk about a mixed reality assurance. It's a human safety, that human facing the issues. And second, we talk about the federal learning. This is the data facing issues. So by addressing this safety, resilience, and privacy together, when we can build the AI system that can be truly trustworthy. Okay, thank you for your listening.